let's consider this example. We have a circuit that has a 1 farad capacitor that is already charged to 100 volts. And then when we close the switch, this is the switch, we are going to discharge it. We have two setups. In one setup, we are going to discharge the capacitor through two light bulbs that are in series. In the second setup, we are going to discharge it through two light bulbs that are in parallel. The question is, which system will be the brightest? Which light will stay on longest? Which light consumes more energy? Okay. These are interesting questions. Okay, first, parallel and in series. Now, if each light bulb has a resistance R, the overall resistance of this circuit is twice R. So the time constant for this circuit is twice R times C. For this one here, two resistors in parallel, if they are the same resistor, their equivalent resistance is half of R. So the time constant for this circuit is R over 2 times C. So if I call this time constant 2 and this is time constant 1, time constant 2 is 1/4 of time constant 1. Now, what about the maximum current? Maximum current is the voltage across the capacitor over the resistance of the circuit. So the maximum current, in this case, let's call it I1, is going to be VC, the 100 volts when it is fully charged, over twice R. In this case, the maximum current, let's call it I2, it's going to be VC. This is not the current through the light bulbs, the current out of the capacitor. VC over R over 2. Which is twice VC over R. So you notice here that I2 is actually equal to 4 times I1, which will make, if I call this I2, which will make each of the currents I light twice I1. Okay. So now which system will be the brightest? Obviously, it's going to be the system where I have the larger current. The larger current is in system 2, so it's going to be system 2. Which system will stay on the longest? Obviously, it's going to be the one that has the larger time constant, which is system 1. Which light consumes more energy? Okay, and this is a trick question, because where's the energy where would the energy come from? The energy is going to come from the capacitor in both times. These are going to be bright, but for a short time. These are going to be dim, but for a long time. The energy is the same amount of energy from the capacitor in both cases. Let's consider this question here. The two switches are closed. What is the final charge on the capacitor after the switches have been closed for a long time? Okay, that's when the capacitor is fully charged. Now, to do that, we need to remember a few things. Both switches are closed, which means that we can have a current here, let's call it I, a current here that's called IR, and a current in the capacitor, IC. If the capacitor is fully charged, IC is 0. Then I is equal to IR. Okay? Now, let's write Kirchhoff's voltage rules. Let's do it first for the rightmost loop. So in this case, going counterclockwise from the top of C. So I'm going to go to minus Q that I'm looking for over C plus RIR is equal to 0. Or let's just call it I since IR and I are the same. Now I'm going to do the outermost loop counterclockwise as well. For the outermost loop, I'm going to start at Ri plus twice R times I minus E is equal to 0. So from the second equation, we get I as equal to E over 3R. Now, if we plug this in the top equation, we get Q over C is equal to R times E over 3R. The R's cancel out, and we get Q is equal to E C over 3. So that's my answer. Okay, now we have a different circuit. We have R here, capacitance here, twice R here. This is closed. So it's like when we had S1 and S2, but both of them closed. And it is asking what's the voltage across the capacitor after the switch had been closed for a long time. Okay, this is the trick here. Because this one here is closed while we are charging, the voltage across the capacitor is not going to be equal to E. We have to find it using the voltage rules. Okay. Now, what's going to happen after the switch is closed for a long time? The capacitor is going to be fully charged and IC is going to be equal to 0. When IC is equal to 0, then the voltage across the capacitor, okay, doing this loop like we did in the previous question. So I'm going minus voltage across the capacitor plus voltage across to R is equal to 0. So the voltage across the capacitor is just the voltage across to R, which is just 2R times I. Let's do the outer loop like we did last time. So for the outer loop, we have 2R times I plus, here, by the way, we are calling it I sub B. So 2R times I sub B plus R times I sub B minus E is equal to 0. So I sub B is actually equal to E over 3R, which is in this case, okay, let me wait and plug it in there, which makes VC is equal to twice R E over 3R. The R's cancel out and we are left with 2E over 3. So 2/3 of E. E is 24 volts. So it's 2 times 24, 48. 48 divided by 3. That gives us 16 volts. Okay, in this question here, after switch 1 had been closed for a long time, it is opened. And switch 2 remains closed. What is the current through the right resistor just after switch 1 is opened? Okay, so we have to be careful here. This is very much like what we did in the previous circuit. Now, the distinction, we have a reverse here. Here I had R and twice R. In this case, we had VC as equal to 16 volts. I don't think we are going to get the same thing in here. Instead of having 2/3, it might be 1/3. Okay, so let's quickly focus on the voltage across the capacitor when we close the switch. We need to focus on the voltage across the capacitor because the current is going to be voltage across the capacitor over R. Because this is open, so this is the only circuit then. So it's going to be the voltage across the capacitor over R. So we need to figure out what the voltage across the capacitor is. To find the voltage across the capacitor, we consider the case when both switches are closed and the capacitor is fully charged. So again, like in the previous question, voltage across the capacitor in this case is going to be equal to the voltage across R, or R times IR. But then we are going to have IR plus twice R I minus V is equal to 0. So I is going to be V over 3R. And I is the same as IR, since the current through the capacitor is 0. Remember, after a long time it is 0. So I go back to VC. VC then is R IR. So it is R V over 3R. So it is V over 3. So if I try to find IR, then it's going to be just this, V over 3R. Actually, I found it here without going back there. Now let's consider what happens in this case. This is a different case from the previous question. In this case, switch 2 is closed all the time. In this case, switch 2 is initially open. Then we open switch 1 and close switch 2. What is the current through the resistor then? Okay. Now, if switch 2 was open initially, that's during the charge, this part of the circuit is irrelevant. If that part of the circuit is irrelevant, the charge in the capacitor, the voltage in the capacitor is going to be equal to V after a long time. The same as the voltage across the source. And that's because the current had nowhere else to go but through the capacitor. So now, when we open S1 and close S2, then it's this V that's going to discharge through R. This V is the full V. So IR is going to be just V over R. And that's my answer.